I know. This is why I absolutely hate this. We live in the desert where there is zero humidity, and these things just will never work. So who decided this was a good idea? No. All right. They all stop.
Possible that it's the board?
That's better. All right. So we're talking about entanglement of the quantum field. Electromagnetic. Okay. And as we've sort of introduced and how we started our discussion last time, is that the entanglement that we have depends on the kinds of degrees of freedom we are looking at. So entanglement is entanglement between different subsystems, and what we call a subsystem in quantum mechanics is what we think about as a degree of freedom from a point of view of a classical dynamical description. And we have different kinds of degrees of freedom. That is to say, the quantum field, when we think about the quantum field, we can think about the quantum field as a many-body system, which consists of particles, okay? So we can have the degrees of freedom of the particles, photons. And the degrees of freedom associated with the particles are associated with their motion, which really is sort of, having to do with the sort of something about the spatial and temporal modes, or the spin, which for the case of the photon is its polarization. So when we think about the entanglement associated with the different degrees of freedom of the particle, they have to do with how the particle is moving, its position, momentum of the particle, or its spin degrees of freedom can be entangled. In that case, it's the polarization. But we can also think about the field as being consistent of waves or modes. And we can think about this is a kind of multi-body effect. And so we can think about for example, the quadratures that are associated with the oscillation of the field. But those oscillation of the field is not the position momentum of the particle, it's the oscillation of the field. And we can think about entanglement between different modes that have their own quadratures, okay? So all of these things in principle can be entangled, and all of them have been entangled and are used in different contexts in different applications and different studies of foundations of quantum mechanics. Yeah?
So when we, let's say, encode a qubit in the polarization, is it polarization of
the particle,
photon?
of a photon.
A photon.
Well, you have two
Can
photons.
It be two photons?
You have two photons, right? So if we want, I could entangle the polarization of the photon with its motion, right? Because I need 2 degrees of freedom. I need a bipartite system. I need 2 parts to be entangled.
Yeah.
So if I'm going to have entanglement, I want to at least think about 2 degrees of freedom.
Okay.
They could be 2 degrees of freedom within the same particle.
Yeah.
Or they could be 2 different particles.
I guess my question is like related to the CGM paper yesterday, but so is polarization a property of a single photon?
It is.
Okay. What if we have two photons?
Then each one has its own polarization, or they could be entangled, and we'll talk about that.
Okay, great.
In the same way, is the spin of the electron a property of one electron? Yes.
Yeah.
But if I want to think about a singlet state, I have two electrons, for example. And I could have a Bell state associated with a qubit, 2 qubits. I need 2 qubits to have a Bell state. Okay, well, so yeah, let's talk about all of that. All right. So, how are we going to create entanglement? Given, if we want to create entanglement, then we need some kind of interaction, Hamiltonian. That will cause an entangling interaction between the different degrees of freedom, okay? And we gotta start with somewhere. We don't have this entanglement to start. Typically, to create it, we would start with something that was like a classical source of light, like a laser beam that's well described by a coherent state, where we really don't have any notion of entanglement in any of the degrees of freedom that we might consider. And as we discussed, the way in which we typically think about creating non-classical light is through nonlinear optics. So the same nonlinear optical processes that we particularly talked about when we, as the workhorse of, say, creating squeezed single mode light, and we didn't talk about entanglement in that case, but we are going to. The most powerful way we can do that is through three-wave mixing. Okay, if we have a Chi2 material, a material with a Chi2 susceptibility, a Chi2 crystal, then that's sort of the best thing we can do to try to make as the sort of first big nonlinear effect, if it's possible. Okay, so we have this crystal, and we talked about three-wave mixing last time, and not last time, but last when we last talked about it, where we imagined we had a pump beam that might be ultraviolet or something like that, or something that might be a nice purple color, and what we then is that we put in some signal, and boy, do I wish I had a red one. It felt like taking a walk and getting me a red pen, I wouldn't complain. But let's pretend this is red. Okay, so I have some signal, right? This color is red, okay? And what we discussed last time is that what will happen is there will be amplification, a parametric amplification of the signal, and also generation of an idler beam that will actually, this will be okay. I actually use a phase matching. Let's say that this is a nice blue color. I think that'll still work. That's my signal, and that's my idler. Okay, and as we discussed, this process of three-wave mixing is most efficient when we have phase matching. So we'll get a exponential, thank you very much. Yeah. we will get the maximum conversion from the pump to the signal in the idler when we satisfy the phase matching conditions. And those phase matching conditions were that the wave vectors added up, and that the frequencies added up. Okay? Those were the phase matching conditions. And that, for example, was a way that we can, say, create a squeezed vacuum state. In particular, in this case, if we would get a squeezed vacuum in the context that we had a degenerate parametric amplifier, especially it's a parametric oscillator, as we discussed some few weeks ago. Now, this process is, this is what is shown here is that I injected a signal, I amplified it, and we generally generate a secondary beam that satisfies the phase matching conditions. That's a kind of stimulated emission, if you wanted to think about it. But what is true is that if I take this crystal and I inject into this crystal just the pump, then what's going to happen is I will also get spontaneous parametric down conversion. So what will happen is I could get one of these blue photons coming out. Let's see, what color is that one? This color. As well as one of these guys coming out in a different direction. Okay? That's known as spontaneous parametric down conversion. Okay? Why is it called down conversion? It's called down conversion because I've converted some of the light at this higher frequency down to lower frequencies. So it's called down conversion opposed to up conversion, which obviously is the opposite. Now, of course, that's not the only possibility that can happen because there are lots of different ways I can satisfy this phase matching condition. So, this was the case where I started with this pump, and I have now this case where I have this blue guy. So the pump is purple. And then I have blue. And I had some orange. Orange has a shorter length. And it adds up, right? So this was one of the cases where I have the pump, the signal, and the idler. What I call signal and what I call idler is completely arbitrary. Typically, we would call the signal the thing we inject, but when they're both spontaneous, which one's the signal, which one the idler, that's your choice. But there are other ways that this can happen. In particular, I might have a situation where I have both of them coming out at exactly the same angle. So I might have this guy, they're both at the same angle, and they add up to half this purple guy. Oh Lord, am I good at this? No. Purple. Okay, so this is another possible phase matching condition that I could have, where the signal and idler are degenerate. And there are a whole rainbow of colors that I could have that satisfy the spontaneous parametric down conversion. So from the point of view of a level diagram, what I have in this situation is that I'm sending in this pump photon, and I'm getting spontaneous emission of 2 photons, which add together to this photon. But there's lots of different ways that that can happen. I could have, this other guy here that is a little bit bluer, and this guy is now orange. And all of them can happen, okay? As long as they satisfy the phase matching condition, okay? So, in this, we can think about this phase matching condition a little bit more carefully. You'll remember that in order to satisfy the phase matching condition, because the wave vector, the length of the wave vector depends on the index of refraction, I can't satisfy this kind of phase matching condition unless the index of refraction is different for some of the different frequencies, the different kinds of beams. So one way we looked at this is the problem of what we call type 1 phase matching, which is the situation where the 2 down-converted have the same polarization. That is to say, the index of refraction is the same for them, but the other one is, for a birefringent crystal, one is ordinary, one is extraordinary. We know we have to have this kind of situation where there is some preferred direction of space, something which is breaking parity inversion, because there's no way I can conserve parity in this 3-wave mixing process. I can't have, this has to have the opposite parity of this if these were parity eigenstates, but then there's no way these 2 photons could be emitted because that would conserve the parity. So these cannot be parity eigenstates. You can't do 3-wave mixing in an atomic vapor. You gotta do 4-wave mixing, okay? But in a crystal, I can have stress and strain, I can break inversion symmetry, and then I can have the situation where I might have, I'd have this guy, which is polarized, say, in the plane, like this, and then these guys, or let's do it the other way around. Let's say these guys, this is, because I don't want to do it, this guy is polarized like this, and both of these guys have the same polarization into the, or out of the board, okay? And then in that situation, I might say this is, if I said a birefringent crystal, this is the index of refraction associated with the, say, extraordinary direction, and then this guy is the index of refraction associated with the ordinary. These guys have the same polarization, but they're opposite to that, okay? All right, so then what I have in these phase matching conditions, because the magnitude of K is the index times omega over C, I have the condition, if this angle here is theta, theta for the signal and a theta for the idler, then I have the equation of motion for this. It says the index of refraction of the pump times omega over C, but C will cancel, times in the, say, cosine theta has to equal the index of refraction. The pump is in the extraordinary, the ordinary direction, omega S cosine of the idler plus the ordinary index of refraction, sorry, signal, idler, cosine theta, idler, and then there's no transverse component of the pump, and I have right? So that's just equating the component along the pump and the component transverse to the pump. And this tells me at what directions these two things can be emitted. These two different colors can be emitted. And what it says is that they're emitted in cones. So, you know, this whole thing, anything on this cone can satisfy the phase matching condition, right? So here's my attempt at perspective drawing, which sucks. Here we are, here's my crystal. And then I send in the pump, and I get these cones out, and the cones come out such that I have, you know, guys like this, and then I have the guys that are in blue, and then the guys, it's the other way around, the blue guys are outside the green guys. And then I have the green guys, and then I have the orange guys, and then I have the red guys. Okay, so I can have spontaneously emitted photons that are emitted in this. That's why on the cover of every quantum optics textbook, there's this picture like in Scully, I meant to bring it, you know, of these rings of colors that are related to entanglement photons. Yeah.
This is subtle and I might be wrong, but
Yeah.
with the way you have theta I defined, wouldn't you want the last term and the sign expression to be negative? So you're kind of
Yeah, no, it depends how I'm defining it.
Right.
If I'm defining it, you know, going from this to that, or the other way around, it
Yeah,
doesn't really
yeah,
matter.
whatever.
It's just however you define it. That's a detail that doesn't matter much. In the end, they come out in cones. Okay. Now, I just to make my life just a little bit easier, I'll draw this head on now. Okay. So here's my different cones. That are coming out of the board. And the pump is blocked. And now the point here is that the wave vector, any one of these is a possible emission direction of a spontaneous photon. But they come in pairs. And they come in pairs on opposite sides of the cone. Okay? So for example, if there is a photon that I pick out with a pinhole, so oops, I put a pinhole and I'm just going to take any photon that comes out of that pinhole, then there is a pair that was emitted at the same time as it, that is this photon. Okay, so those two photons are emitted in pairs. Alternatively, I might have the situation where I have this pair of photons that is emitted, okay? If I put a pinhole here, then the only thing that phase matches it is that guy, okay?
Did you mean it, the photon for the blue one is on the blue curve at the bottom?
Can you ask the question again?
So the photon on the top,
I put a pinhole here,
Yes.
a photon comes out.
Yes.
That's guaranteed that there's gonna be an orange one here.
interesting. Okay.
Because they have, that's the one
Oh, I
that
see, I see. Oh,
satisfies
okay,
the
okay.
phase matching
Sure,
condition.
yeah.
So the two photons don't come out in the same direction.
Hmm.
They come out in these conjugate pair directions and these conjugate pair colors.
Mhm.
However, who says which one has happened? We don't know. In fact, all of the different spectrum and directions that satisfy the phase matching condition are equally likely. More formally, as you remember, we have this Hamiltonian. I better put caps on these things, they're all going to dry out in nanoseconds.
There's a cap on the floor somewhere, isn't there?
So, formally what we had is that the Hamiltonian, was chi2 E, right? The polarization, right? And that, when we put in all of the mode decomposition, when we put in the decomposition, in this case, this is the signal, the idler, and then I have, the pump, which I treat as a classical field, right? So I can annihilate the pump and create one of these, or I could take the sum generation and get to that. So you remember that this is kind of like, something which is going to be some integral over all the possible modes. They have the same polarization, so I'm not going to write down their polarization degree of freedom, but I have the modes of the signal and the modes of the idler such that I satisfy the phase matching conditions. With some constant up front. The three-wave mixing process that is phase matched in this problem involves the annihilation of a pump photon, which we treated classically, and the creation of these two other photons in these other modes that satisfy the phase matching condition. Okay? So, if I start with the vacuum in these other colors, and I apply the pump, then the state that comes out of this system will basically be something like the vacuum with some coefficient plus a 2-photon condition plus 4 photons, ... Okay? Because if I apply this unitary, e to the IHT, I'm going to get a vacuum term, and then I'm going to get a 2-photon term, and then 4 photon terms, etc. Okay? Now, if my nonlinearity is weak, then the dominant non-vacuum term will be this. Okay? And that 2-photon wave function will look like this. To the degree that I have perfect phase matching, which is always an approximation, but it's good when the length of the crystal is very long. Which is to say, the 2-photon component of this, what comes out of this spontaneous parametric down conversion, is a superposition of multiple ways the photons can be emitted as long as they satisfy this phase matching condition. This state is entangled in the motion of the photons. Or that's to say their spatial temporal modes. Let's say which mode are they in? Does everyone, any questions about this so far? So the entanglement, one kind of entanglement that is produced in spontaneous parametric Dampierversion of this type with type 1 is not polarization entanglement because the photons have the same entanglement. There's no, everything has the same entanglement. It's the same polarization. It's polarized into the board. There's no polarization entanglement. But there's entanglement in the motion, which is to say they're entangled in color, which has to do with the length of their wave vectors, and in the direction of the wave vectors, which you might say is something about the spatial modes of the photons. That's one way that these are entangled. Yeah?
You said this side 2 was a good approximation for when the crystal's like long enough? Is that long enough?
Yeah, what I'm saying is that, not that the two-part, the fact that this dominates over this is that this will be, when the nonlinearity is never that strong, I'm mostly going to get perturbation theory. So
okay. Gotcha.
So I think it as the identity plus I times that. That's a good approximation because the nonlinearity is weak.
That's what you mean.
The thing I was saying about the crystal being infinitely long is under the crystal being infinitely long, I get perfect phase matching. When the crystal is not that long, then this doesn't have to be exactly true. But when the crystal is very long, then I get this is a good approximation. Yeah.
Is it accurate to say, like, I'm thinking about this in terms of like cascaded mixing processes?
Okay, that's a different deal.
That's a
I
completely.
mean, you're talking about periodic polling when you're talking about cascading? Because yeah.
I know for like chi-free materials, for
Yeah.
like a big frequency code,
Yeah.
it's just like cascaded four-wave mixing. Is it accurate to think, can you do that one, I guess, in chi-2 materials? But
I'm not sure, Brandon. I'm not really familiar with the jargon. What I thought you were referring to is one way to get something that looks phase matched is what's called periodic polling, which has to do with the fact the material doesn't have a chi2, it has a chi3, but that's maybe not what you're referring to. Yeah, but we could talk about it afterwards. I'm not really an expert in that stuff. Okay, but let's talk about the nature of the entanglement that we see here. In particular, let's suppose, as I suggested, I'm going to put a pinhole that blocks out all the photons except a very narrow band of directions. It doesn't be super narrow. I want to have some spectrum. It's going to be basically there's going to be a kind of paraxial beam coming out of here that is basically blue, and a paraxial beam that comes out of here that is basically orange, plus with some spread around it depending on the size of the pinhole. Okay. So what is the nature of that case? What is, in that situation, my two photon state? Well, I can think about it in the following way. It sort of will, I'm going to have, let me see, let me write that, get my notation straight here. So now I'm very much restricting the direction of these guys. I'm going to say that's well defined by the pinhole. But the length of the vector is not necessarily well defined, right? So I'm going to think about that length of the vector in terms of thinking about the frequency of these two that's related to the length of the wave vectors. And they have to add up to the pump, okay? There's going to be some distribution of signals that come through that pinhole because I'm not making it a point. So there's some, depending on the size, the size of the pinhole, there'll be a spread of different colors that can come out. I'm going to ignore the spread in the directions because it's going to be fairly well defined by that. And then I'm going to just use, instead of second quantized notation, well, it doesn't really matter. There's one photon in this guy and one photon in that. This is my, sorry, not S. Dyslexia strikes again, 2. Okay? Now, I just want you to look at that for a moment and think about what this means. This is sort of like, if you think about the frequency, it's related to the length of the wave vector, which is linked to the momentum. This is saying something kind of like about the center of mass momentum of the two photon pair, which is fixed, okay, in this way. And if I wanted to think about, instead of the frequency, I can think about the time at which the photon arrives at a particular detector, then this, I can write this in the opposite, in the conjugate temporal variable. That's to say, if I time bit this, and I think about it as arriving at a particular time at the detector, doing that Fourier transform, in the temporal modes, as we discussed in the past, I have something that has to do with the relative time that the two photons arrive at detectors that are equally away from the pinhole, which is the inverse Fourier transform of the spectral function. To the degree to which I approximate this as flat, it's not going to be that flat because it's the pinhole, but the degree to which this is very broad, this is very narrow, approaching a delta function. So what is that telling us? What it's telling us is on these two modes, the photons are moving, at the speed of light, right? And they could arrive, where they are is determined by the probability amplitude. What it's saying is these two photons, when they're born in the crystal, their separation at birth is determined by this amplitude. To the degree to which that approaches a delta function is to say those are twins. They were born at the same time. But what's their birthday? They were both born on the same day within some nanoseconds of one another. But when were they born? Well, that will depend on the inverse Fourier transform of their center of mass, where they are, and that's completely undetermined. That is to say, when you have this kind of process, to the degree to which the crystal is very long, we don't know, the photon could have been born at any time when it was inside that crystal. And to the degree to which that crystal is very, very long, we don't know when the photon was born. So this is just like the EPR state, where you know the relative position very well, but you don't know anything about where its center of mass is. Yeah?
How long are these crystals in practice?
I think there's some centimeters,
Yeah, that's pretty big, I guess.
but you know, relative to, you know, the optical,
Yeah.
yeah. So that's interesting. What this is, so there's a kind, this is sometimes called time energy entanglement. Another way we can write the state in first quantization, where we only have one photon in each mode, so we don't have to worry about one photon at that, or I say that I can think about the time where they're both born at the same time. So this is a kind of entanglement that exists in this system. Now, it's interesting that this gives us the possibility of seeing unique two-photon interference. So let me think about this crystal again. And let's put in this guy, and let's say I put pinholes over here to ensure that I only get, well, I don't even want them to be the same color, because it's more interesting when they're not. So let's say we got the blue guy and we got the orange guy. Okay? And now what I'm going to do is I'm going to put in a beam splitter over here, and I'm going to let this go through a Mach-Zehnder interferometer. Looks like that. So this photon can go around this interferometer by either reflecting, going like this, or going like that. It's an unbalanced interferometer. And there's going to be a similar thing over here. Let's see, this guy is going to be reflected. That, oh boy. Like that. Okay? And then I'm going to have, at this side over here, I'm going to have detectors. And I can look at coincidence, or I can look at singles. Okay? So does everyone understand what's going on over here? I have these pinholes. I picked out these particular phase match photons that come out in one of the terms in the pairs with some spread. Okay? The two-photon wave function that comes out of this is going to look something like that, with, depending on the spread of how big the pinhole is, tells me sort of the spectrum that can get out of this thing. Okay? So now the question is, firstly, to the degree to which, if I looked at the singles counts, and I looked at it, I have two different paths over here, okay? So I have a, in this guy, I have a L long for this guy, and an L short for this guy. So L short is this path length, and L long is that path length. And there's a similar thing over here. There's going to be an L short for this second photon, or maybe this I'll call the signal, and the, oh boy. Ugh. Okay, so that's not a good idea. We'll stick with 1 and 2. So this is the long, and this is the short. So for this second photon, there's a long path and a short path. All right? So now I ask you the following question. If I were to look at my singles counts in either of these detectors, and I looked at them as a function of the path difference between this, what would I see? So if I looked at, I'm going to now just plot as a function of delta L, short minus long, or long minus short, for either one, and let's just say that these two guys, for the sake of simplicity, let's say that they're both the same exact interferometer. So the length of this guy is the same as the length of the long guy here, and the length of the short guy here. These two are the same interferometer. They're both unbalanced, though. So now I ask you, if I look at the singles rate as a function of delta L, what would you expect to see? Well, let me ask you a different question. If I send a pulse of light, so here's I'm going to draw over here, the interferometer again. And I send a pulse of light into this interferometer. Am I going to see any interference on this interferometer? Well, it depends.
It depends on the
Probably no. It sort of depends on what is the path length difference compared to the coherence length of this pulse. The question is, if the timing, if it's such that if it went through the short path that went here, here's the garbage can. Oh!
Do another splice.
Yeah. Okay. This one works, yay! Right, so this is the short and this is the long, right? If the size of the pulse, it will come out faster on the short path and it will be delayed, come out later, there's no overlap, right? So a question is, are these individual photons broadband? The answer is it depends on the size of this pinhole. If the pinhole is big enough, then yes. And we're approximating that when we have this case. And in fact, so I'm going to put a little aside over here. The famous Hahn-O Mandel experiment was one where they took this crystal and they wanted to measure how broadband the photons were. So what they did is they took this guy and they took whatever, 2 photons coming out. And now what they did is they took instead of looking at singles counts, they retroreflected it and then put them on a 50-50 beam splitter, and they looked at coincidence counts. This is the Hahn-O Mandel effect that we've studied in the homework. And when the 2 photons arrive at the beam splitter at the same time, what we know is they either both go this way or that way, and we never see coincidence. And what they measured as a function of this little delta t as they move this around was the famous Hahn-O Mandel dip. And this represents the duration of the photon, which was, I don't know,
Small.
I'm trying to remember, 4 nanoseconds, okay? So it's broadband. It's like, it's bizarre because this is, for the people who know this jargon, this is all CW, okay? You have a pump, there's no mode locking, there's no Q switching, there's no nothing, it's just one color, but the spectrum of things means that the photons that come out, if you put the right pinholes, are pulses. Now you don't know when those pulses happened, but if you find one pulse, you're going to find the other. Okay? So now I asked you, so what I'm looking at is the counts here as a function of this thing, and what we just said for the singles, that's to say either one of these, it's the amount of counts I get is independent of this delta L. However, what about the coincidence counts?
So they can both take this short and the singer can both take the long.
Exactly. There are 2, as we know, importantly, that what we've been taught by the great Dr. Feynman is that if there are indistinguishable processes that both lead to the same outcome, then to find the probability of that outcome, we must add the amplitudes and then square. And as Cole correctly said, there are 2 different ways that we can get that. I can either go, this guy goes through this and this guy goes through that. That would correspond to, because they're born at the same time, plus or minus 4 nanoseconds, then they're going to arrive and be in coincidence, plus or minus within the coincidence window. But there's no saying that they were born at that time. There's another process by which they were born, which was later, and that would correspond to them taking this path. So they can both go short, or they can both go long, and both that's indistinguishable to the degree to which we have no information about from at the time of their birth, because it's entangled. And so what we would get in that situation is that the amplitude for 2-photon coincidence short plus whatever the amplitude is for long, which we can loosely say is e to the I phi, okay, the signal went through the short path, and the idler went through the short path. And then there's an amplitude for the signal to go through the long path, and an amplitude for the idler to go through. Oh boy. Horrible indication. This is not the way I'm showing. Okay, so 1 is the upper interferometer and 2 is the lower interferometer. And they can both go through the short or they can both go through the long. Okay, so let's look at the probability for coincidence then, which is the square of the amplitude. I'm going to get this squared plus that squared, and then I really got some factors out here for normalization. So it's going to be 1/2, 1 plus the cosine. Let me get this right. Yeah, the signal delta L in 1 plus the idler delta L in 2, where delta L is equal to L minus short. Okay, but if we just look at the interference between these guys. Okay, let's rewrite that. I have one more board, so that's nice. Not that guy. Not that guy. That's good. So the probability of coincidence, if I just rewrite the cosine term as follows, because the pump is equal to the signal plus the idler frequency. So I can write this as delta T1 plus delta T2 over 2 plus delta S minus delta I, delta T1 minus delta T2 over C, where delta T is whatever path length difference I'm talking about over C. Okay. So, what's delta T1 and delta T2? That's the path length difference in the first interferometer in units of time compared to the path length difference in the second interferometer in units of time. So the question of what's the difference in the imbalancing of those two? If those two things were unbalanced in exactly the same way, well, that term would be 0. It's never going to be exactly true in the experiment. However, this term is not going to matter much because really I need to average over all the signal frequencies, and that's very, very, very broad to the degree to which I assumed a broad spectrum. So the degree to which the spread in the frequencies is much, much bigger than the difference in the imbalancing in, then this term won't contribute much. Okay. And so what one sees in this experiment, then, in the terms of those counts, are interference fringes. But those interference fringes go, if I write this in units of C, like this, where the period of oscillation is the pump. That is to say, I see interference not in what's happening in any one photon going through an interferometer, but interference between the two photons going into two interferometers, and those two photons either going like this or like that. And because those two paths pick up a different phase, and there is an indistinguishability between which those two, and I add them, I'm going to see oscillations of amplitude that are related to the two photon energy, not the one photon energy. And I see that the period of those oscillations at the period associated with the pump, not of the signal nor the either. That was an experiment done by my good friends and my lab mates, Paul Kwiat and Ephraim Steinberg in Ray Moonchild's lab in 1990 something. All right. Now I should also mention that the photons that are created in the spontaneous parametric down conversion are not only entangled in terms of their color, which has to do with the time at which they are emitted, their motion along that direction, but also their transverse motion. As I say, the spatial mode, if the photon is like this, the photon must be moving down in the other transverse direction. So there is, in addition to the time energy entanglement, the photons, oh Jesus. Oh, it's closer. What are you thinking? Okay, yeah. Humor me.
Shoot light through a pinhole.
What's that?
Trying to shoot light through a pinhole.
Oh, God. All right.
I would try to get out there, you get, guys to walk through another thing like this.
I want to practice.
One just landed on the floor in front of you.
God.
Okay. Maybe that one's dead. Yeah, that's good.
We just throw garbage at it.
Yeah, do that. Just do it. So there's also what we call spatial mode entanglement. In spatial mode entanglement, what we would say is that there is a two-photon component here which depends on the transverse so if I write K as having a component parallel and a component perpendicular, this is parallel to the pump. So the question really is, what's the nature of the two photon wave function associated with motion perpendicular to its direction? That's also entangled. It's a longer story. People sometimes call that orbital angular momentum entanglement. We can think about the modes that are entangled as being associated with the photons going in a spiral pattern. They're Legendre Bessel modes. Okay. In fact, there's a kind of hyper entanglement that exists in this system. So I wrote the wave function like this, but really it's this tensor that. Okay, just doing that for the TV. So, meaning that they're both entangled in their motion along the direction of propagation and entangled in their motion perpendicular. You can have at the same time, because my tensor product structure involves both the motion along the direction of propagation and the direction perpendicular, they can be simultaneously time energy entangled and spatial modes entangled. Yeah?
So what if noise hurts one kind of entanglement more than the other? Does it affect the other entanglement?
No, because they're not entangled with one another.
Yeah, because
Yeah.
they're independent.
So they're separable.
So they're just separate Hilbert spaces in some sense.
That's right. They're in the tensor product space, there's a tensor product of motion along here and motion along here. Now there's one other degree of freedom of the photons that we haven't talked about, and that's their spin.
But wait, there's more.
Yeah, but wait, there's some more. And then there's more.
How many qubits can photons hold?
Oh, that's another good question. Hyperentanglement is about that. So, the notion of encoding multiple subsystems, of course, firstly, the motional degree of freedom is not a qubit. It could be a qubit,
Yeah.
right? So I can, and people do think about that for cryptography, thinking about multiple spatial modes, not just two, and I can have qubit entanglement. It's also with the time bidding. So I have basically, I have three motional modes, right? So I have 3 degrees of freedom associated with motion along here, motion along there, and motion along there. They can all be separable. And then the polarization. The polarization is a qubit, though. Now, to deal with the qubit mode, I'll just quickly mention that. I guess we'll have to pick this up over Zoom. God, I really thought it was going to go great. Anyways, those stupid markers. So we can think about now type 2 phase matching. The reason we didn't have entanglement in the, or at least this is the first way it was envisioned. The reason we didn't have entanglement between polarizations here is that both photons were born with the same polarization. So there was no, that just factored out, okay? But if I think about type 2 phase matching, then I can have a situation where the signal is, say, ordinary, and the idler is extraordinary. I can arrange the so-called optical axis of the crystal in such a way that I get a phase matching condition such that, and I'll make the pump, say, ordinary. So I'll have the pump be at one guy and the signal at that same kind of thing. Then the idler has the other. Oh boy. And similarly, So that's the phase matching condition, where these guys have opposite indices of fraction. Now it turns out, in this kind of situation, what happens, unlike that, is that I have an offset of cones. When I have type 2 phase matching, there are the photons that come out that are, say, this with ordinary polarization come out on one cone, and the ones that have extraordinary polarization come out on a displaced cone. And it looks kind of like this. Okay, so I have two kinds of cones, ones that are associated with polarization that is in one direction, and the other cone that's associated with polarization in the other direction. So this set of cones is, say, the extraordinary axis, and this set of cones is associated with polarization. Okay. Now, importantly, what we see is there's a very special condition right here. Yeah.
So you draw it where they're like perpendicular? Are they necessarily perpendicular?
They are. They're necessarily perpendicular because they are the two different eigenvectors associated with the birefringent crystal. Okay, so the birefringent crystal has two orthogonal directions that are associated with an index of fraction that doesn't change. If you started with any other thing, you'd get a birefringent ellipticity rotation. But along these directions, there's no change. Now notice that there's these two this is special case right here, where the photons have the same color, they're in the same direction, but I don't know whether the photon right at that X is polarized like this or is polarized like that. These two photons here, if I were to look at the two photon wave function now for this guy, so let's call this, what do we say? This is horizontal and this is vertical, okay? Horizontal and vertical polarizations. I can have a situation where I created a photon in that mode that is horizontal, or I can create the other case. So in this case, one of them comes out in this K1. It's on this first guy. Or, and then its pair comes out on the other one. Or vice versa. But since they both come out in the same mode, I can factor that out. And in first quantization, what I have is HV plus VH tensored into K1, K2. Because I don't know which pair was admitted to which cone. This is a way to make polarization entanglement. Now, we're out of time, but I'll just mention, and we'll pick this up next time. It's not a very bright source of entangled photons. I mean, it's as bright as any of these others. You have this pinhole, you know, in this guy. You know, you're throwing away a lot of photons. But it would sure be nice if you could take these two emission patterns and move them on top of one another, such that at every point you have a blue with this direction and a blue with that direction. Then everywhere, at every point in every mode, you have polarization entanglement. And that was another lovely experiment done by Paul Kwiat, which I'll explain to you next time. All right? Very good, everybody. Have a good rest of your day.